So in this lecture, we will do two things. One is we will see different kinds of gears and for what kind of power transmission tasks they are useful. And second, we will study gear trains, which are the real assemblies for power transmission. So the simplest kind of motion transfer, power transfer, power transmission is between two parallel shafts. And in that case, the simplest gear pair that you can have is per gear, in which the teeth are parallel to the axles. So typically, the contact ratio is a little more than 1.4, 1.3 times. Contact ratio means at any time, how much, I'm not telling how many, I'm telling how much of this gear teeth engages with the partner. I said how much because it is not 1, 2, 4 kind of thing. It is 1.3, 1.4. So 1.3 basically means that maybe one tooth is totally engaged in its central duration of engagement, and the other one has just left. I mean, just leaving. Other one is just leaving, or other one is just engaging on the way. Kind of. Okay, so typically, the ratio turns out to be 1.3, 1.4. And one bad thing. I mean, this is simple. That is one good thing. Now, one bad thing about spur gears is that one pair of teeth should be not axis. One pair of teeth. That is one tooth of this gear and one tooth of the other gear come in contact at the same time all along the full length. So that means the entire load that is to come on the tooth of the driven gear comes all at the same time. Okay? So that is impact load. Okay? So you would not like that to happen. The remedy for that is helical gear, in which the teeth are cut along helices on this, and similarly on this, there bicycle. So in this case, what happens is that when the tooth comes in the zone of engagement, one part of it gets engaged, okay, and slowly the rest is taken out. By the time the old one is going out of the engagement zone. So for this side and as well as for this side. So in this way, the impact issue is resolved in the case of helical gear. However, a new issue now comes because in the spur gear, the force transmitted from one tooth of a gear to one tooth of the other gear was perpendicular to the axis, and that's why there was no axial force. Now what happens is that there is a little pressure angle, that is the force acts on an inclined direction, say something like 15 degrees to the perpendicular to the axis, and therefore a 15-degree sine 15-degree component of the force transmitted to the tooth would come in the axial direction, which is bad because then this shaft, on the shaft, the gear will experience a force in this direction, okay, or and in turn the shaft will experience a force in that direction. So that axial thrust is something. So on this one, if the axial thrust is this way, on this one, axial thrust will be this way, other way. Okay? So this is a new problem that comes from helical gear, which was not there in spur gear. And to remedy this, people worked out a way double helical gear. That is, in the entire width of the gear, have half of it cut along this way, single, and the rest helices cut it the other way. Similarly, here, that way, the lateral thrust because of this part and the lateral thrust because of the other part will get counterbalanced. So this is called double helical gear and also as herringbone. Herringbone because you see the backbone bits. I mean that kind of a picture. So this is called herringbone. Now, in the entire terminology, in the case of gears, not only these kinds, the other kinds also, which we will discuss later, there is a very funny thing that sometimes people use the word gear and wheel interchangeably. And sometimes the smaller of the two machine gears, people refer to as pinion. Okay, what is pinion? Now, pinion is also a gear. Now, when you say gear and pinion, then you mean the larger gear and the smaller gear. Or you can say wheel and pinion. That is larger gear and smaller gear. The smaller gear is often referred to as pinion. And the larger gear is called a gear, sometimes as wheel. Now these are sort of colloquial, but also used in wheel. Now some more kinds of. There is something called spiral gears. Spiral gears is nothing of a different kind. The gears are just spherical gears, but mounted on shafts for power transmission, which are not parallel but skewed. So like this. So they are mounted in particular orientation so that there is a contact and possibility of force and motion transfer from one to the other. However, this contact is precarious because unlike other gears, this is not even line contact, this is contact. And therefore, spiral gears are used for transmission of only small amount of power. Okay. Spiral gears are also called cross helical gears because two helical gears are put in cross. Okay. Another kind of gear is bevel gear, in which you see the shape is conical. Okay. So if you extend these feet, you will actually end up describing a cone. So, and this also. So the center, the vertex, the common vertex of the two cones is the point at which the two axes. So this is a cone of the semi-vertical angle gamma 1, and this one is of gamma 2. This kind of gear pairs are called bevel gears. Now, these are for power transmission between intersectors. In particular, if you find gamma 1, the semi-vertical angle of one of them, the larger one typically, is a right angle, then this tooth at the end would turn out to be at right angle to that. Like in that case, sometimes this larger one is also called round gear or round gear, and which has some special utilities in certain sectors. And round because if this becomes perpendicular, I mean, if this is standing and then this becomes perpendicular, then on that, whatever gets mounted, that operates as a crown. So, wholesale. So, another special case is rack and pinion, where the pitch radius of one of the partners tends to infinity, then basically it becomes straight. and that is called lag. And this pair is called latency. So as you can understand, this is the arrangement to transmit power between a rotary motion and a sliding motion. So if you rotate this, then this advances. Or if you advance this, then this rotates. Another pair is 1 and 1 here, or 1 and 1 here. Again, you see here we have so 1 is basically a helix. So you cut a helix on this cylinder, that is the 1. And in a along a skew perpendicular axis, you mount the other wheel or one wheel. Okay, it should be one wheel, not one slash. One wheel or one wheel. So one and one wheel. In that, what happens is that you get a very high transmission ratio because one full turn of the one results in just advance of the one gear or one wheel by just one wheel. That's on 6 speed. So in that case, it will be only gear reduction of 1 by 6. But it could have had 32. In that case, it would be 1 by 30 gear reduction. So high transmission ratios this way or that way, you get by 1 and 1 gear. Now we come to gear. The gear train is basically a combination of gears to transmit power from one shaft to another. In a simple gear train, every shaft carries only one gear, and power may be transmitted from gear 1 to B, then from B to C, or C to D, and so on. I mean, or alternatively from shafts. Shaft A to shaft B, shaft B to shaft C, and so on. Two pairs of. So, in this case, calculating the speed ratio is very simple. Suppose you transmit from A to B, B to C, C to D. Okay. Connected one after the other in a series. Then you want to find out the output by input speed ratio, and that would be omega d by omega c, omega c by omega b, omega b by omega a. And for each pair on the way, you can work out the speed ratio. Omega d by omega c is mc by md, where mc and md are the number of feet in gears c and d, similarly. And then mc and md in between, the intermediate ones get cancelled out, and finally you get another, which you would have got directly also if you have connected them directly. But directly you could not connect because of certain other reasons. On the way you wanted to go out a letter out from somewhere, or the distances of the axles were not appropriate for this purpose and so on. So in this case, finding the speed ratio is very simple. In the case of a compound gear train, on the same shaft, more than one gears may be mounted. Okay. For example, here you see gear B and gear C are on the same shaft. They rotate together. Okay. With the same power. So now in this case, if A is a driver which drives B and C automatically moves with that, and then C drives B, and you want to find out output to speed ratio, omega D by omega A, then we will say that omega B by omega A and omega B and omega C are the same. So then here you will say omega D by omega C. And This one is this individual, and this one is this individual. And then when you simplify it, here I have put the minus signs because here I have shown the axes to be all parallel, and in that case, positive and negative signs you could say in a consistent manner. Okay. On the other hand, in this case, I did not put the signs. Sign had to be suitably interpreted according to the context. Because, for example, if there are double gears, so one axis and the other axis are not parallel, so you cannot say this is opposite. So, which one you will take positive, which one you will take negative, which senses, that you have to decide and put in the formulation for each one separately. So this is one kind of gear train, simple gear train, it has something. This compound gear train, it has something. There is a third kind, which is the interesting, and that is epicyclic gear train. It typically has at least one epicyclic gear, the axis of which moves on a cycle, on a circle. The axis moves on a circle, the axis is not fixed. Now, why is it called epicycle? You know what is epicycle? When a circle rolls on another circle, then any point on the rolling circle executes a curve which is an epicycle, which is called an epicycle. The curve epicycle got great awareness very early in history because of the study of the mechanics. Okay. So anyway, so now here it is called epicyclic gear because the axis turning in a circle, any point on the periphery, that is where the gear tooth is, that moves on a circle that itself is turning over a circle. So that executes an epicycle. So an epicyclic gear train is typically a 2D figure. Look at this example. In this example, there are two gears. P is the simple gear and Q is the epicyclic gear. And as it is, the Q gear might fall off. So that it does not fall off, you connect its center to the fixed pivot O with a rigid arm. Okay. So now there are how many links are there? One is the frame, second is gear P, third is the arm, and fourth is the gear P. And what are the pairs? At O, there is a double joint because the frame and the gear P and frame and the arm. There is a double joint. At CQ, that is center of Q, there is a simple joint between the arm and the gear P. Apart from that, there is a higher pair profile contact between P and Q at the gear P. So these are the pairs. Now, if you use the formula for degree of freedom, you will find 3 into 3, because minus 1 is not 3, minus twice, one simple joint and one double joint. So for double joint, you get 2 and minus the number of higher pairs, because every higher pair can be replaced with, I mean, this formula we actually found. We get it. Okay, but I will remind you how we get up this formula, minus 8. That for every higher pair, you can replace that higher pair with one extra link in between and two simple pairs at the two ends. So that way, um, 3 will get added here and 4 will get subtracted here. So eventually 1 will get subtracted. So that's the minus 8. So using this formula will give you everything. And you can see that actually for this schematic. If you fix P to frame, okay, arm can rotate related to the frame. So then the arm and the cube, gear cube, can rotate as it rotates, the arm rotates, and the gear cube will roll over this fixed gear cube. Okay. So 1 degree of freedom. Now the other way, you fix the arm to fit. You fix the arm to fit. Then arm is always horizontal. Then in effect, this point CQ gets fixed, and point O is anyway fixed. Then gear P and gear Q to operate as an ordinary pair of gears. Still 1 degree of freedom here. So that means if you lock 1 degree of freedom, another degree of freedom still remains. So that means to begin with, we had 2 degrees of freedom, which we get from the calculation. Now, to analyze the motion of such gear trains completely, you would typically give an X motion to one of the freedoms, that is say this one, there is motion of P related to the frame, and then give another motion Y to the other degree of freedom, say motion of A related to the frame, and then add up the corresponding effects on each of the links, each of the gears, and so on. So superimpose these two effects in terms of linear combinations of X and Y, and then whatever conditions you have got in hand, you apply those conditions to determine the other quantities, other motions which you wanted to implement. So this is very simple actually. You need to go to the examples in the textbook to get hold of it. Now, there is one very important and interesting applications of recycled gear trains, and that is in the automobile defense ships. So when you take your two-wheeler along a turn, the inner wheel and the outer wheel move at different speeds, and that different speeds will be provided, will be allowed by the device called differential. So the shaft from the engine, the propeller shaft comes and sub in a gear, with which a big gear called the crown gear is connected, okay, which is the full gear. So this crown gear is connected to that, and that is actually free to turn related to this shaft of the right wheel. Okay. Now, from the crown wheel or crown gear, one extension here and another extension here. This holds the shaft, this also holds the shaft. And these two shafts have two so-called planet gears, C1 and C1, C2 mounted over same size, okay, same full degrees. Okay. And between C1 and C2, there are two gears, B1 and B2, which are vertical. Okay. These are actually connected to the shafts of the two rear wheels. Now, during state motion, what happens? That motion X comes from the engine to A. And after conversion at this gear ratio, the crown wheel B rotates with the ratio into X, whatever ratio turns out to be, okay, that Rx. With that Rx, crown wheel B rotates. And this one, C1, C2, D1, D2, all together for the time being, like a rigid assembly, done with B. Okay? Because you see, this is held at the top, this is held at the bottom. And as B turns, this whole assembly is going to turn. Okay. And that is how this wheel and this wheel, they move at the same speed as the crown wheel B and go forward. Now during a turn, what happens? That because of the steering, you have arranged to change the direction of the motion. Okay. And then The road conditions give the necessary little extra force in one direction and a little extra necessary force in the other direction. And this arrangement allows that extra differential motion. How? Then, apart from A getting motion x and transmitting to B in the ratio R with the ratio R, in addition, C1, C2 turn to a motion y. So, say this one turns like this, so comes, this end comes up, so B1 turns like this end goes down, so this goes down, and this end comes up, and then this one goes up, this one goes down. So here this goes up, this goes down, here this goes up, this goes down. So D1 and D2 turn in the opposite direction. Okay. Rotate in the opposite direction because of the spinning of the C1 and C2 line plates. I mean, I need not say because in conformity with that. So apart from the x motion that B is getting, D1 and D2 are getting equal and opposite motions in the two opposite directions along the same axis, one forward and one backward. And from the motion of B, forward motion is anyway coming because at the time of spinning, C1, C2 do not stop turning with the ground wheel like this. Okay, so that also goes on. So now the real degree of freedom motion is actually found. And that is why the two rear wheels, D1 and D2, get the final motion as Rx plus R prime Y. Okay. And this is the way by which you achieve different motion, different rate of turning of the two rear wheels. So there are some interesting problems, numerical problems like that in the textbook. Look at that. Now till now we have concentrated on motion only. And there is also little to look at the plots. Now these are very simple, straightforward kinematics and dynamics stuff. If the entire motion system, if the entire system runs at constant speed, then constant angular speed, basically angular speed, then there is no angular acceleration on any other components, and then there will be total moment applied on the entire assembly should be zero. So two inputs and one output, so three components which interact with the environment. So the corresponding moments together should be zero. So these are the three input and output. Further, if friction losses, etc., can be adjusted, then we will say the corresponding total power also from the three sources, from and to the sources and destinations, depending upon what is output, what is input. M1 omega 1 plus M2 omega 2 plus M3 omega 3, that also will be zero, that also will be balanced. Okay. So input moment into input speed plus output moment into output speed plus the other input moment into other input speed, whatever it is. Okay. So together they will also be zero. Now often it happens that the entire mechanism operates in single degree of freedom mode with one of the inputs suppressed. Say omega 3 is kept zero. So in that case, basically this motion input is given, it's not suppressed, it is given as zero. Okay. That's it. So in order to hold it fixed, M3 will be not zero. There will be a holding torque. Okay. So M3 becomes the holding torque, it is called the holding torque in order to keep it fixed. So these are the three conditions that may appear when you try to work out the relationships among the torques operating with the different components of the vehicle. So I think that completes the little discussion on gears which we needed in this course. So we stop here. So Thank you. So this actually, according to the plan of our semester course, this covers the entire